These notes are over the normal force. So if we have two different situations involving the same object, so an apple that weighs 0.225 kilograms, where one is free falling towards Earth and then one is sitting on the table, they're going to be experiencing different types of forces. Okay, so they're both going to experience the force due to gravity, okay, because gravity here on Earth is a constant, and so it's going to be feeling the acceleration of negative 9.8, okay, but because this one is falling, it only feels the force of gravity, whereas this one is sitting on a desk. So it's not accelerating, okay, and so because of that, we need a net force of 0 in order to have the object not accelerating. Because if you remember from Newton's second law, the equation F equals ma, right? If our acceleration is 0, that means our net forces need to be 0. Okay, so in order to have a net force of 0, if the apple is experiencing the force of gravity in the downward direction, it needs to have an equal but opposite force acting upon the apple in the upward direction. Okay, and this force is known as the normal force. Okay, so if you remember from our saying that all forces come in pairs, that's Newton's third law, the force pushing down on the tabletop must be met with an equal but opposite force. So the normal force is the reaction force. So just like Newton's third law. Okay, so the normal does not mean regular or ordinary. It just means perpendicular. Okay, so it's going to act at a 90-degree angle to the surface the object is on. Okay, whereas gravity is just going to be pulling the object down towards Earth. Okay, so here we have the following situations. The normal force is always going to be perpendicular to whatever surface the object is being pressed against or anything like that, or sitting on. Okay, so the normal force is kind of the compensator for forces. And so what happens is providing whatever surface the object is sitting on or being pressed against, the normal force will increase as force applied increases. So here's kind of an example of that. So if we have a book on a desk and you were to put your hand on the book and apply a downward force, okay, the book isn't going to accelerate through the desk. And that just means that the forces are all balanced. So if you have your book just lightly resting, or your hand lightly resting on the book, okay, the forces that are being felt by the book or being applied to the book is one, gravity, okay, and then also the light force of your hand resting on the book, okay, and so if we were to add these two together, they're going to be equal but in the opposite direction of the normal force. If we were to apply more pressure, downward pressure, to the book, okay, so we have a greater force being pushed onto the book plus the force felt by gravity, that's still going to be equal but opposite direction to the normal force. So as we apply more pressure, the normal force is going to increase. So you might notice that your hand kind of starts to hurt as you press harder and harder because the normal force is increasing with your increasing pressure on the book, okay? Because the book is still not accelerating due to the normal force being strong enough. Now, if you were to press hard enough that the desk or whatever it is can no longer apply an equal normal force, what will happen is it'll break or it'll start to fall back down towards Earth, the book will. Okay, so the steps kind of to solve problems using the normal force. First, you want to draw the free body diagram and label all the forces. And especially for these problems, just expect to label an F of n if there is a surface involved. Okay, so if it is preventing the object from accelerating, or if there is if it's not a free fall object. Okay, and then number 2, create a net force statement and solve for any unknown variables. Okay, so remember that the net force statement is the net force equals m times a, mass times acceleration. So for example, the net force for like this problem here would be the F of your hand, the F of G, and the F of N. So all of these together would equal the mass times acceleration. And for the most part, the acceleration is going to be 0, so we would set them all equal to 0. Okay, if the surface is on an angle, you will usually need to find the x and y components of F of N, so you have to break down those components using the trigonomic ratio. So that's kind of like whenever we were breaking the forces down before. Okay. One key thing to note as well, that the normal force isn't always in the upward direction, so it's just dependent on the surface that is non-moving. So for these examples, question A, an elephant of mass 4,700 kilograms steps onto a platform. So what's the normal force acting on the elephant? So the first thing we need to do is draw the FBD for the elephant. So here we have the elephant with the kilograms labeled inside, and then we're going to draw the force of gravity here, which our force of gravity is going to equal the mass times the constant of gravity, negative 9.8. And then we have the upward force of the normal force, okay? Because on the platform, the elephant isn't falling through the platform, okay? So our acceleration is going to be 0. So we set up our F of net equals mass times acceleration, okay? So our F of net is going to be broken down into F of n, our normal force, plus our F of g, the gravitational force. Okay, so the acceleration of the object is 0, so 0 times the mass is just going to be 0, so 0 equals F of n plus F of g. If we put F of n on the other side, so subtract it from both sides, and then divide the negative to this side, so now we have negative F of g equals positive F of n. Okay, and then plug in our F of g, so the mass of the elephant times the acceleration due to gravity. Okay, and what we find is that the normal force is 46,060 newtons up. For part B, what's the normal force of a magnet being held to the chalkboard with a force of 1.5 newtons. Okay, so the important thing here is drawing the FBD and determining where the chalkboard is. So here I have drawn that the chalkboard is here on this side. Okay, so the force being applied by the magnet to hold the magnet there in place on the chalkboard is 1.5 newtons. Okay. What's nice about this problem is they've already solved the force, so we know that if the magnet is not moving, the normal force is going to be equal but opposite. So if the magnet force was holding it to the right or pulling it to the right, the normal force is going to be applied in the left direction, so 1.5 newtons to the left. If you are helping to install an 11 kilogram decorative beam to a ceiling, you apply a force of 170 newtons upwards to hold the beam in place while you wait for your coworker to install the beam. What's the normal force acting on the beam? So first we draw the FBD for the beam. So here we have the beam with the mass written inside of our sphere here, or circle. And so then all of the force acting upon it. So we have our applied force, our upward force, as we're pushing the beam upwards of 170 newtons. Okay, the beam is going to be feeling the force of gravity. So here I'm actually solving for gravity. So the force of gravity equals mass times the gravitational constant. So 11 times 9.8, it's 107.8 in the downwards direction. And then we have our normal force, which is preventing the beam from going through the ceiling, basically. Okay, so the surface is above the object, and so prior to drawing the F of n, the upward force is greater, but we know that the acceleration is 0. That's what makes it necessary for the F of n. Okay, so the net force felt is going to be all three of our forces added together. So the applied force, the normal force, and the gravitational force. Okay, so remember, F of net is going to be equal to m of a, or m times a, so mass times acceleration, which we know that acceleration is 0 because the beam isn't continuing to move upward or downward. Okay, and so our applied force is 170 newtons. Our force of gravity we calculated was negative 107.8, okay, plus our F of n, which we don't know. So if we solve for F of n, we will get that the normal force is negative 62.2 newtons, and that would mean it's in the downward direction. For this last example problem, we're dealing with scales, and so scales are a common question whenever they're talking about normal force. Okay, so you see this a lot, questions like these a lot whenever you're taking any other physics class and they're exploring normal forces. Okay, so the scale's reading called the apparent weight. Okay, so all of these terms are interchangeable. So the apparent weight, the normal force, and the scale reading, they're all meaning the same thing. Okay, it's always in the same as the normal force acting on the person. Okay, so we have those pairs of forces. So consider a 75 kilogram person standing on a scale in an elevator. Hypothesize the strength of the normal force relative to the force of gravity, and then find the normal force. If the elevator is stationary, so we'd have an acceleration of 0. The elevator accelerates upwards at 0.25 meters per second squared. The elevator accelerates downwards at 0.6 meters per second squared. Or the elevator is moving upwards at a constant velocity. Okay, remember, if it's moving at a constant velocity, it has 0 acceleration. Okay, so for part A, I drew the free body diagram. So here is my person, my 75 kilogram person. They're experiencing the force of gravity. It's going to be negative 735. So I took the mass, 75, times the negative 9.8 to find the force of gravity. Now you'll notice the force of gravity experienced by all of these situations is going to be the same, okay? Because the acceleration due to gravity is not changing because we're here on Earth. It's a constant, so it's going to be constant throughout the 4 problems. Okay, so that's the force of gravity, and then we put the force of the normal force, okay, which prevents the person from falling through the floor. Okay, so for this one, they have an acceleration of 0. Okay. For this one, they have an acceleration of 0.25. For this one, we have an acceleration of negative 0.6. And then for this one, it's going to be 0 again because we're moving at a constant velocity, so no acceleration. Okay, once again, our F of net, which is Fn plus Fg, is equal to ma. And so they just kind of switched it here. And so we're going to use this equation here in order to solve for the different problems. Okay, so for the first one, our m times a, 75 times 0, is going to be 0 on this side, equals our f of n, which we're trying to calculate, plus f of g. So minus, because it's a negative, 735 newtons. So then when we solve for F of n, we get that the normal force is 735 newtons upwards. Okay, for the next one, this one is accelerating. So we're going to take the mass of the object, 75 kilograms, times our acceleration, which is positive 0.25, equal to our F of n minus the gravitational force. Would be plus the gravitational force, but it's a negative, so minus 735 newtons. Okay, when we solve for F of n, we get that it's 753.75. Okay, so as we move up, the normal force is increasing. Okay, for part C, we're accelerating downwards, so a negative 0.6. So I have that plugged in for the acceleration times the mass of the object equal to F of n minus 735 newtons. When I solve for F of n, it is 690 newtons up. Okay, so notice it's less, the person experiences less weight whenever they are going downwards, accelerating downwards. Okay, and it's similar to that free fall experience. So they have these flights that you can do where you kind of get into this air hangar and they basically have the air hangar do a nosedive, and it makes you feel weightless inside of the cabin of the aircraft. So it is using this principle that when you have downwards acceleration, the normal force lessens. Okay, and then for part D, because we have an acceleration of 0, it's going to experience the same amount of force that we had in part A, so it's going to have a normal force of 735 newtons. Okay, so here is just a summary of kind of what I went over for parts A, B, and C. So when acceleration is 0, the normal force is going to equal the gravitational force, just in the opposite direction. Okay, if acceleration is upward, the normal force is going to be greater in quantity than the gravitational force. But if acceleration is downward, the gravitational force is going to be greater than, the magnitude will be greater than the normal force.